Welcome back to the classroom. This is Mr. Wong speaking. We are looking at Module 3, Waves and Thermodynamics. Inquiry Question 3, Sound Waves, and we're going to cover the following dot points. We're going to investigate the behavior and model standing waves on pipes or in pipe instruments. And we're going to also look at the relationship between distance and sound intensity. Now this is going to be split into two videos, so this will the one about intensity of sound will follow after we talk about the standing waves. Right, for your textbook reference, you're looking at these pages here. So let's get started. So in our previous lesson, we talked about two fixed ends, one fixed end, one open end. What type of pitch harmonic are we going to get there? Okay, so that's what we talked about there. We said that if we generate a pitch or a higher tone pitch, we have a shorter wavelength and we have a higher frequency. We also said depending on the type of instrument we use, we get a different type of harmonic being formed. So in our previous lesson we talked about if there were two fixed ends or two open ends, what type of note will we form here? We said the first frequency we form, or the fundamental frequency, first harmonic, will generate half a wavelength pitch tone. If we go to the second harmonic, our first overtone, that'll be a full wavelength. And if we go to our third harmonic, we get 1/1.5 wavelengths. We generated a general formula for the length of string that is generated for that wavelength as n divided by 2 times lambda. We also looked at one fixed end or one open end and what would come to that in terms of the harmonics. We know that the harmonics will go up by odd numbers. So if we have our fundamental frequency, so frequency 1, then we go to frequency 2, our first overtone, our harmonic is 3. If we go to the next successive frequency, our second overtone, our harmonic will be at number 5. You can also see that it goes up in quarters and halves. So we start by, instead of having half a wavelength like the two fixed ends, the one fixed end starts with a quarter of a wavelength, goes up by a half to 3/4, and then goes up by a half again to 5/4. You can work out easily what harmonic you're in simply by looking at the value over the 4 there in terms of wavelengths. Came up with some general formulas to describe different types of musical instruments. So if we have the flute, which is two open ends, then we use the following formulas here to work out the frequency and wavelength and velocity of the sound that's being made. If we're dealing with one fixed end or one open end pipe, like the clarinet, we're going to use the following equations to help us do the calculations here. Okay? That's just to recap everything. So what you can understand and appreciate now is music is about generating vibrations. These vibrations, depending on the type of music you form, is sound wave or standing waves. You're trying to produce these different harmonics of standing waves, different overtones of standing waves that will provide you with a different type of pitch you're dealing with. Another way we can work out how fast the wave is traveling in the string is just this little equation here. So what we have is the velocity of the wave in a stretched string depends on two factors. The tension of the string, so say if you're playing a violin or guitar, and also the mass per unit. So how heavy is that piece of string per meter? Those are the two main factors that will affect how fast that sound travels along the string there. Okay, that's what we're looking into. You can see the units. So tension is a force, so it's given in newtons. Mass per length is obviously, mass is kilograms. If we're doing per length, so it's divided by meters. And then meters per second, obviously, m times s to the power of 1. Okay, so what can we work out in terms of the sound, how fast the sound is being generated? We can work out that if we increase the tension force, tension on the string, we get faster vibrations, so a higher pitch. If we have thicker wires, we can decrease the velocity. So if we have thicker wires, this will go down, so we get a lower pitch. If we make the wires more thin, we can also generate a higher pitch. If you have a guitar at home or any kind of a string instrument, have a look, pick it up, and actually play a note. When you play the note of a thicker wire, do you hear shorter or lower pitch? If you play a note on the thinner wire, do you hear a higher pitch? Let's try and show this in terms of frequency as well. Okay, so what we have here is frequency equals to velocity divided by lambda. We know that we're dealing with two fixed ends, so just substitute lambda for 2 times L, the length of the wire, and we know the velocity is this equation here, so we can substitute that through. Okay, this is the working out here. I might just quickly do it on the side as well, just so you see what we're doing as well. So to start ourselves off, I'm going to move 2L outside this box here. Okay, I'm going to move it out and make it frequency equals tension force ml times 1 over 2L. Now the reason why I want to do this is I want to incorporate the 2L into this equation here. Okay, so that's what I'm trying to do. Okay, so what we get our tension force, and to make this fit into here, obviously you can also move the half out, so we can move half times L, get the squared, rearrange that. Okay, so going on from what we have here, I might just move the working out to this side to use a bit more space. This bit here can be a little bit misleading, so I'm just going to show it again. We have an equation at the tension over ml minus 1 inverse times 1 over 2L. Now the thing I'm going to do is I'm going to move this L minus up here, because this L minus, okay, represents 1 over L. Now if it's obviously, if the minus sign is coming at the bottom of the fraction, obviously it means if I rewrite this, so L minus 1 would be the same thing as writing L, because it's just the inverse of the inverse. Okay, so I get my equation at T m times L. Okay, it is also squared, don't forget, so just make sure you move that along like so, over 2L. Okay, now I'm going to move the 2 to the other side, move that at the front. We get half T of m square root of L over L. What we also know is L is the same thing as saying L, the square root of L times the square root of L. So that means if I can just simplify this, I do a little cancelling out, I can get it as Tm times 1 over square root of L. Rearrange all that together, you get this equation here. Remember, the reason why this is occurring is because of that. So if I cancel one out, I still have square root of L left. So this is the formula of frequency on a string instrument. If you don't know, obviously, the particular harmonic you're dealing with, this is another way of working it out. Examples that we showed here. Okay, next one, it says the lowest E string on a guitar has a fundamental frequency of 82.4 Hertz. Okay, so we know the frequency there. If the guitar string has a vibrational length of 600 millimeters, so that's 640 10 to the power 3 meters. Oh, actually, quick correction, minus 2, everything's right. Yep, that's all good. This one should be 2, no, that's all good. moving on. If the guitar string has a vibrational length of that, what is the speed of the particular wave? Okay, so what we need to work out is the velocity, and we also need to work out the length of the string that we're dealing with here. Okay, that's what we need to do. So to complete this question, quite simple. So we know the length of vibration of the string is L. So the wavelength we're going to generate is 2 times 640 millimeters 10 to the minus 3 divided by n. Now because we are at the fundamental frequency, n is equal to 1. So 1 is our value. Okay, so the value we get for the wavelength is about 1.28 meters. From there we can then substitute it in our formula here. So we know that we want to find the frequency, so just rearrange that. We know that the speed of sound is approximately 330, 340 depending on the value of the data sheet. We'll go with 340. So we have 340 divided by the wavelength of 1.28. That is our frequency there. So we'll go to the answers shortly. And the low E string on average guitar has a mass per unit length of that value there. What is the tension of the force stretching the string? So I know the velocity of sound wave is 340. I want to find the tension, and I know that the length per unit force is this value here. So what you need to do is square both sides. So it'll be 340 square equals to tension force over our mass per length. So 340 square times this value here equals to our tension force. So let's look at the two values and what do we get? Alright. Okay, so let's have a look at this question here. So we know that the fundamental frequency is F1, so that's 82.4. We know that the vibrational length L is 640, which if you convert that into meters is given to you by this value. So if we substitute that into our equation, 2 times 640 times 10 to the power negative 3 over 1, because that's our fundamental frequency, we have a wavelength of about 1.28 meters. Now if I want to work out the speed, substitute into our formula, V equals F lambda. Now F, that's already given to you, F1, the fundamental frequency is 82.4, times our wavelength, 1.28, and we get a velocity of around about 105 meters per second. Okay, that's the speed of our length. Now if we follow on with the same question, we want to work out the tension force of this guitar. So what kind of tension force am I using to generate the speed on the string? Okay, we know the mass length is that. We already know what the value for velocity is, that's 105. We want to find the tension force, and we substitute in our mass per length unit. So all we need to do is 105 square to move it out, square both sides. Then what I have is 105 squared times 6.38 times 10 to the power of 3. That'll be our tension force. So the answer to that is, once I put in my calculator, 70.3 newtons of tension force there. Okay, so that's how you do that question there as well. Okay, so that's what we got with the standing strings and the standing waves. If we look at this question here, I just want to briefly go over how does this component work. So this is part of the homework. If we have a look, although it says it's a wavelength of 1, it's not actually true. You can actually see that you're generating half a wavelength there. That's for our first frequency. In terms of antinodes, that is 1 antinode there. So that's our fundamental frequency, the very first one. This, you can see, these are fixed ends, okay? So if it's fixed ends, they go up by, in terms of the harmonics, you're going up by 1. So the second node we create is the second harmonic, the third one is the third harmonic, 4, 5, and 6. If we count the number of antinodes, we have 1 antinode there, 1 antinode there, so that gives us 2. Okay? In terms of the frequency, we have twice the frequency there. Okay, it's more frequent. If we look at the wavelength that we generate, that's a full wavelength there. And we continue on with the amount of antinodes. That's frequency of 3. This one we have is 1.5 wavelengths. So 3/2 wavelengths there. So follow on using the same pattern to fill in this table as homework. That kind of summarizes what we need to do for this lesson when it comes to harmonics for strings. But do make sure you continue on to the next video, which is talking about intensity of sound as well. Okay, so I'm going to leave this video here for now. Please have a go at the video where it comes to intensity of sound, and we will get to that very shortly as well.